everybody. Today we're going to learn how to extract infinite energy from a black hole. So, first, some background. There's this principle in quantum mechanics called the Pauli exclusion principle. What it says that two fermions are basically protons, neutrons, electrons. They cannot occupy the same state. What it means is that two fermions basically what it means that two fermions cannot occupy the same place. They cannot be in the same place. So two electrons cannot be in the same place because of this principle. So what happens is, as the star is being crushed in, these two electrons come so close, and because of this principle they cannot go much further. They cannot go any further. This outward force which prevents these two electrons from reaching the same position is called degeneracy pressure. And this is what holds up the sun after it has exhausted all of its fuel. And this star is composed of this degeneracy, this exclusion principle of electrons. This star is called a white dwarf. So, what about high mass stars? Stars with more than eight times the mass of our sun. Then things are quite different. The star not only fuses still hydrogen, it actually fuses still sorry. The star not only fuses still carbon, it fuses still iron and nickel. It fuses still iron and nickel. So what happens after it fuses still iron nickel? So what happens is, whenever you fuse whenever you fuse iron, it's it basically doesn't give out more energy than it takes in, right? It's an endothermic process. So the more you fuse iron, the lesser the total energy becomes, right? So the star again starts contracting, and it doesn't work for this exclusion principle. What happens is, the proton captures the electron. They both merge. This is called electron capture, which is basically proton plus electron equals neutron. So neutron is another fermion. Okay. So what happens is, there are two possible outcomes for a big star, right? One is a neutron star. Neutron star is basically a star filled with neutrons because of this electron capture, and it is supported by the degeneracy pressure of neutrons. Like, it's the same Pauli exclusion principle, but for neutrons this time. That's a neutron star. The other star is, the other outcome is a black hole, right? So what basically happens is, there's another quantum mechanics principle called the Heisenberg uncertainty principle, which basically says that you cannot measure one quantity. No, sorry, you cannot measure two quantities with 100% precision. If your measurement is more precise on one quantity, the lesser precise you know the other quantity. Right? If you know an atom's speed more precisely, then the less precisely you know the atom's position. So using this uncertainty principle, we can overcome the Pauli exclusion principle, and we can collapse every single atom in a star to a single point. called the singularity. This single point is called the singularity. And the area, like there's a boundary beyond which if you go inside, you will also get crushed. To sing along with all other things, along with the entire star, you get crushed to a singular point. And that boundary is called event horizon. So what happens is, as the star is spinning, we all know stars spin. And because stars spinning, stars are huge compared to black holes. As stars contract due to the conservation of angular momentum, even black holes spin much faster. Black holes spin so fast, right? So spinning black holes have a weird property. If this if this is the event horizon, as the black hole as the black hole is spinning, let's say in this direction for simplicity, what happens is the black hole spin is so fast and black hole's gravitational pull is so huge that the space time surrounding the black hole also gets dragged around it. The space time itself, the space time fabric on which everything happens itself gets dragged around along with the rotation of the black hole and due to the rotation of the black hole. This is called frame dragging. This dragging of space time is called frame dragging. If you want to learn this more intuitively, I have left a link in the description and the info card. You can go learn it betterly, more intuitively. So what basically happens is, so how do you extract energy from this? The A physicist by the name of Roger Penrose. Another fact: this this frame dragged space-time region is called the ergosphere. Ergosphere. So if you somehow venture into the ergosphere, you cannot go back. I mean, you won't fall into the black hole, you just keep orbiting it. No matter how much energy you use, you cannot go out of it. Because there is no there is no such thing called backwards. Because everything is going around it. The space in which you are itself is moving around. You're not moving. The space on which you are itself is moving. So there's actually nothing called moving backwards. But what happened? But a physicist by the name of Roger Penrose gave an interesting theory. Let's imagine that this is event horizon. The second circle is ergosphere. So let's say that you have a spacecraft, a two-part spacecraft. This is the first part. This is the second part. If you were to send this spacecraft into the ergosphere, it will keep on rotating, orbiting, right? But what if, while orbiting, Penrose said, if you separated these two spacecrafts, one would go inside the black hole, one would come out. Due to some fancy maths and the conservation of angular momentum, this is true. And fun fact, the coming out part, part of the spacecraft has more energy than the energy it entered with.